Hi everybody. In the two previous videos, we introduced the nuts and bolts of quantum mechanics and also connected partition functions to properties that we can actually measure, like average energy, heat capacity, and pressure. In the next few videos, we're going to see how these ideas play out for real systems, starting in this video with monatomic ideal gases, just isolated atoms, and in the next two videos moving on to more complicated molecules. While the focus of this video will be on monatomic ideal gases, I'd like to say a few things about molecules in general first. The energy of a molecule can be thought of as the sum of different types of energy: translational energy, rotational energy, vibrational energy, and electronic energy. The pictures on this slide show what we mean by this. Translation is when an atom or molecule moves in space, rotation is when a molecule tumbles around, vibration is when a bond goes back and forth, and electronic energy refers to the energies of molecular orbitals. In a molecule, these types of energy are mostly independent of each other. In other words, a molecule can be thought of as being in a quantized translational energy level, a quantized rotational energy level, a quantized vibrational energy level, and a quantized electronic energy level, without thinking too much about the interactions between them. This isn't entirely true. Rotational and vibrational energy levels, for example, do depend on each other to some extent. But in our discussion, we can think of these different energy levels as being independent of each other. For some perspective, I'll say that these energy levels are arranged on this slide from closest together on the left to farthest apart on the right. This is something that you might have already known to some extent. For example, rotational spectroscopy uses microwaves, vibrational spectroscopy uses infrared radiation, and electronic spectroscopy uses UV and visible radiation. So from left to right on this slide, it takes more and more energy to excite these quantized energy levels. The other thing that I'd like to point out about these different types of energy is that throughout our quantum mechanics course, we already developed models for these different sets of quantized energy levels. For translational energy levels, we can use the particle in a box model, where the atom or molecule is the particle in a macroscopic box. For rotational energies of a molecule, we can use the rigid rotator model. For vibrational energy levels, we can use the harmonic oscillator model. And for electronic energy levels, we can use some form of molecular orbital theory. Maybe Huckel theory, maybe a modified particle in a box model, but some type of molecular orbital theory. In the previous video, we spent some time looking at the partition functions for distinguishable particles, where we had multiple particles in a system whose energies added to each other to make a total energy of the system. And we showed that for those distinguishable particles, the partition function for an entire system was the product of the partition functions of the individual particles. In other words, when the energies added, the partition functions multiplied. In this case, we're not talking about different particles whose energies are adding together. We're talking about a single particle, a single atom or molecule that has different types of energies that are adding together: translational, rotational, vibrational, and electronic energies. But it turns out that the result is the same. When we have energies that add together, we have partition functions that multiply. So the total partition function of an atom or molecule that has different types of energies that add together is the product of the individual partition functions, the product of translational, rotational, vibrational, and electronic components of the partition function. From those ideas, we can kind of see where things are headed. We can find the individual partition functions, the translational, rotational, vibrational, and electronic partition functions, from our quantum models. We then know that the product of those partition functions is the total partition function of an atom or molecule. And based on the ideas at the end of the previous video, we can then use that total partition function to find measurable properties of the atom or molecule, like average energy, heat capacity, and pressure. And that's basically what we're going to do for the rest of this video and for the two videos that come after this. For increasingly complex systems, we're going to build up from quantum models to partition functions to measurable properties. And we're going to start in the rest of this video with monatomic ideal gases, just isolated atoms. As we said, in general, a partition function can be a product of translational, rotational, vibrational, and electronic components. But for a monatomic ideal gas, for example just an isolated helium atom, I'd like you to spend some time thinking about which of these terms actually contribute significantly to the total partition function. I'll give you a few seconds to think about it. The first thing that we can say is that for a monatomic ideal gas, we really don't have to worry about the rotational or vibrational components of the partition function. That's because an individual atom really can't rotate or vibrate. That can only happen when there are multiple atoms connected in a molecule. Although there are different electronic energy levels in an atom in the form of atomic orbitals, it turns out that those atomic orbitals are much farther apart in energy than kBt, unless the temperature is many thousands of degrees. So at any reasonable temperatures that we're going to be looking at, only the electronic ground state has significant occupation. So the electronic partition function is approximately 1, and we really don't have to worry about it. That means that it's really only the translational partition function that we need to think about for monatomic ideal gases. Translational levels are really close together. Remember, translational energies can be modeled by a particle in a three-dimensional box, where the particle is the atom or molecule, and it's in a macroscopic box. When we're talking about particles that are much heavier than electrons in really big boxes, those translational energy levels are going to be really close together, so a huge number of them are going to be occupied, and we do need to think about that translational partition function. So for monatomic ideal gases, we can think of the total energy as just the translational energy, and the total partition function as just the translational partition function. For the next few slides, we're going to work through the math and see where that leads us in terms of the measurable properties of monatomic ideal gases. I should say that for the next several slides there's going to be a lot of math, so I would really encourage you to slow things down and make sure you're comfortable with each step. We'll start by finding the partition function. The quantum mechanics model for the translational energy levels of an atom is the particle in a three-dimensional box, and we'll use a box with edge length A. The energy levels in this model look like this. Translational energy equals h squared over 8ma squared times the sum of squares of three quantum numbers, nx, ny, and nz. M is the mass of the particle, in this case the atom, and the three quantum numbers can each independently range from 1 to infinity. Although it's not crucial for this lesson, if you want a reminder of where this expression came from, you can refer back to our last particle in a box video. In general, as we've seen, a partition function is just a sum of Boltzmann factors. When we introduced partition functions, we were always just adding up 3 or 4 Boltzmann factors. In this case, because there are an infinite number of translational energy levels, it's actually going to be an infinite sum of Boltzmann factors. In this case, a triple sum where each of the 3 quantum numbers go from 1 to infinity, and it's a triple sum of e to the minus beta times the translational energy. In other words, a triple sum of the Boltzmann factors. In the next step, I'm just going to substitute in for epsilon our particle in a box energies. So I substituted for epsilon our expression h squared over 8ma squared times the sum of squares of the quantum numbers. This looks pretty daunting to solve because it's a triple infinite sum, but fortunately the mathematicians have already done the hard work for us and we can just follow along. In the next step, we can notice that when we have a sum of squares of the 3 quantum numbers in the exponent, we can split up this Boltzmann factor into a product of 3 terms in nx, ny, and nz. We can then split up our triple sum into the product of 3 single sums in nx, ny, and nz, because single sums are a lot easier to solve than triple sums. Next, notice that these 3 terms are all basically the same as each other. The names of the quantum numbers are different in each term, but it doesn't really matter whether our index is called nx, ny, or nz. If the term is otherwise the same, its value is going to be the same. So we can take each of these 3 terms and just call the index n rather than nx, ny, and nz, and recognize that we're going to have just one term raised to the 3rd power. This infinite sum is still difficult to solve, but we're going to use a trick that's a pretty good approximation. For the translational energy levels of an atom at any reasonable temperature, many levels are going to be populated. The energy levels are so close together that we can basically treat them as infinitely close together and continuous. That means that instead of treating this as an infinite sum, which is really hard to solve, we can, to a very good approximation, treat it as an integral, which can be solved exactly when we look it up in an integral table. So rather than solving this infinite sum, we can treat it as an integral with bounds from 0 to infinity. And we can look it up in an integral table. This is the integral of a Gaussian function, and its solution is written here. As one last step, I'll point out that this expression has an a squared raised to the 3/2 power, so that's the same as a cubed. We had said that we were looking at a cubic box of edge length a, and now we've seen that there is an a cubed in the partition function. It turns out that we can say in general that this a cubed is actually the volume of whatever container this atom was in. So I'm going to replace that a cubed with a v. So here we go. We have our partition function of a monatomic ideal gas atom of mass m at temperature T in a box with volume v. Now that we found the partition function, we can find the average energy of the atom. Recall from the previous video that average energy is equal to kBT squared times the partial derivative of ln Q with respect to temperature. Since we now know Q for a monatomic ideal gas atom, we can go through this math to find average energy. First, we want to take the natural log of the translational partition function at the top of the slide. Think back to the log rules that you probably learned at some point in a math course. When you want to take the ln of something raised to a power, you can bring that power out front. So the ln of something raised to the 3/2 is 3/2 times the ln. Also remember that when you want to take the ln of a product of a bunch of terms, you can actually turn that into a sum of natural logs of each term. What that means is that we can rewrite the natural log of the partition function as 3/2 times ln t plus a whole bunch of terms without temperature in them. This at first seems like kind of a careless way to write ln q, to say that it just has a bunch of terms without t. But notice that we're about to take a partial derivative with respect to temperature, and when we do that, all the terms without t are going to go away, because the derivative of a constant is 0. So in the next step, we can say that the partial derivative of ln q with respect to temperature is 3 over 2t, and when we combine the temperature terms, we can say that the average energy of a monatomic ideal gas atom is 3/2 kBT. This is an important result. One interesting thing to notice is that the average energy of a monatomic ideal gas doesn't depend on m. In other words, it doesn't depend what type of atom we're looking at. The average energy is 3/2 kBT regardless of what element it is. I also want to point out that this is a result that we're going to see from a completely different perspective later in the course when we talk about kinetic molecular theory. But for now, we got to this result starting entirely from quantum mechanics. We used quantum mechanics to find the translational energy levels of a particle in a three-dimensional box. We used those energies to find the translational partition function, and then we used the partition function to find the average energy of an atom. If the average energy per atom is 3/2 kBT, then the energy of a macroscopic sample per mole is just that times Avogadro's number, so that's going to be 3/2 RT. Notice the notation used here. When the textbook talks about molar quantities, quantities per mole, it often uses these overlines. So this overline E, referring to energy per mole, is a type of notation that you're going to see a fair amount in the coming videos. If we know energy, we can pretty easily find heat capacity, because heat capacity is just the derivative of energy with respect to temperature. So that means the constant volume heat capacity of a monatomic ideal gas is 3/2 kB per atom and 3/2 R per mole. The last thing I'd like to do in this video, just to further demonstrate the power of what we found here, is to find the pressure of a monatomic ideal gas, even though we already know what it should be from the ideal gas law. We saw in the previous video that the pressure of a macroscopic system can be expressed as kBT times the partial derivative of ln capital Q with respect to volume. This is a capital Q because we're talking about a macroscopic system of many particles. But what we know for a monatomic ideal gas is lowercase q, the partition function of one atom. So let's recall how lowercase q relates to capital Q. Because a gas consists of indistinguishable particles, we can approximate capital Q as lowercase q raised to the n power over n factorial. When we then take the natural log of q to the n over n factorial, we get n times natural log of q minus ln of n factorial. In other words, n times ln q minus a constant. And since we're about to take a partial derivative with respect to volume, that constant is just going to go away. So we can rewrite this as n kbt, swinging the n out front, times the partial derivative of ln lowercase q with respect to volume. Now we can just plug in our lowercase q partition function and go through the math. Since we're about to take a partial derivative with respect to volume, we mainly just care about terms with volume. So we can rewrite ln q as ln v plus a bunch of terms without v, because q is just a product of v and a bunch of terms without v. Then we take a partial derivative with respect to volume and get n kbt over v. That expression is equal to pressure, and if we just swing around the volume term, we can rearrange that to say PV equals capital N kBT, where capital N is the number of particles and kB is the Boltzmann constant. So that's the same thing as saying PV equals lowercase n, the number of moles, times R, the gas constant, times T. And that, of course, is just the ideal gas law. We've already seen the ideal gas law, but it's pretty powerful to see that we can get there starting from quantum mechanics. Here's a review of some of the major results we arrived at in this video for monatomic ideal gases. The average energy of an atom is 3/2 kBt, so the molar energy is 3/2 RT. The heat capacity per atom and per mole are 3/2 kB or 3/2 R. And we showed that we can derive the ideal gas law for a monatomic ideal gas from the particle in a box model and the translational partition function. That's all for now. In the next video, we'll build up these ideas to include rotational and vibrational motion in diatomic molecules.